Hello, one. So we are going to continue with the third part of the number 22's. So this is number 11. So this is from 2014 AMC 8. So a two-digit number is such that the product of the digits plus the sum of its digit is equal to the number itself. What is the unit digit of this number? So like if you have no idea, you can just kind of explore something. Like you can just take one of these numbers as your unit digit and guess your like 10th digit of your choice and see which one does actually satisfy the given condition, which you can actually get the answer anyway. So sometimes choices are going to be like available to use, but for now, let's not use that. So we are given a two-digit number. So I'm going to say this is AB. And when you say AB, that means usually A times B, but in this case, that's AB as two-digit number. That is equal to the product of digits. So I'm going to use a times, like now the product plus sum of the like the product of the digit plus sum of the digits. So which means A plus B plus A times B has to be a two-digit AB. So again, this is not A times B, this is two-digit number. So I will just write this as like 10A plus B. So because that is the tens place, and that will give us A times B plus A plus B. So luckily, these guys nicely cancel each other. So 10A is equal to AB, so which I can write it as 10A is A times B. So since A and B are digit, that is not like, A is not 0, B could be, but there's no choice for 0, so there's no concern either. So A is not 0 because that's the 10th digit of two-digit number, so it shouldn't be 0. So B will be like, I mean, 10A, there was plus A as well, actually. Maybe I cannot do this immediately. So that is plus A. Subtract A, so that will give us 9A equals A times B. Now I can divide by A. So the 9 will be our B. And that is actually unit digit of the number. So that is 9. So again, if you couldn't say this immediately, you can just use the choices and guess the 10th digit. Based on this, it doesn't matter, which is going to work with any numbers anyway. So that is number now 12. On June 1st, a group of students standing in rows with 15 students in each row, which means the number of students in total should be multiple of 15. June 2nd, the same group is standing with all of the students in one long row, which means the total number, whatever that number, should be in that row. There is one row only. And June 3rd, the same group is standing with just one student in each row, which means if you have 25 students, that means there are 25 rows because each row has one student. And June 4th, the same group is standing with 6 students in a row, which means the number of students in total should be multiple of 6. And this process continues until June 12th with different numbers of students per row each day. So we did 1, we did like 6, we did like different numbers. So the number of like, however, on June 13, they cannot find a new way of organizing these students, like which means the total number of students should be a multiple of 1, multiple of 2, multiple of 3, multiple of 12, but not multiple of 13 anymore. So we are looking for something that has 12 different divisors. So because if you have 12 divisors, then you can make a different number of like rows every time, 12 different times, but otherwise you cannot. So when you have 12 divisor idea, then you can just immediately cross these guys because those doesn't have that many divisors, so that probably has. So which is like, I can list if I want to, which is, let's say 30. When you divide by 1, so that's 1, divide by 30, that's 2. So if I divide by 3, which is going to be 20, divide by 4, which should be 15, divide by 5, that will be 12, divide by 6 will be 10, and there is 6 right here, 6 right here, that's 12 divisors. So which means 60 is the answer. That's the smallest number. So if there was no choices, like, or if you are looking for a little bit more like larger numbers, maybe it might be a bit harder to decide that 60. So if you know the number of divisor, you actually can find the number itself without really having the choices. So by using the counting divisor approach. So just quick recap, like if you have, let's say, n, okay, equals, let's say, p1 to the e1, p2 to the e2, all the way pn to the en. So let's say n is a number, and then this is the prime factorization, p1, p2 all are just the prime numbers, e1, e2 all the way to the en is just the exponent. So number of divisors, I will say number of divisors is like positive divisors is going to be e1 plus 1. You add 1 to each exponent, e2 plus 1, and multiply all these numbers, en plus 1. And this is how you find the number of divisor, which is something you can take a look at more, how, why, and this actually works. I'll add more stuff in the description about this, because this is important. So now we have 12 divisors, which means when you multiply the powers after adding 1, you should get 12. But make sure, like, if you're, let's say, 2 and 7, right? This has 1 and this has 1. When you add 1, you get 2. When you add 1, you get 2, which means you multiply at least 2's to get 12, which means 12 can be written like 2 times 6. That's the smallest we can. Or I can have 2 times 2 times 3. So these are the two different ways that we can get 12 divisors. So 2 and 6, 2, 2, and 3 are going to be powers of the prime numbers in the prime factorization after adding 1. So based on this, you can just find, like, your numbers should have two different prime divisors or 3 different prime divisors. These are the 2 possible cases. One case, you can say 2 to the 5th power times 3 to the 1st power. I choose 2 and 3 because those are the smallest prime numbers, because we are trying to find the smallest one. So when you add 1 to this guy, that's 6. When you add 1 to this guy, you got 2. So you get 2 and 6. So that is the smallest number with 2 different prime numbers. So that will be 32 times 3, which is 96. So 96 is also another number that has 12 divisor. But as you see, that's not a choice. But let's use this guy now. And if you want to use 2, 2, and 3, so you have 3 different prime numbers. So these are the smallest one, but I'd like to get the powers as well. So these are the powers after adding 1, and then this is the largest one. So which means one of these should have the 2nd power, and other 2 should have the 1st power, because we're going to add 1 to get these numbers. So that means I will just take the 2nd power right here, 1st power right here, 1st power right here. So that will be 4 times 5, 20, times 3 will be 60. So that will be the smallest number we can get. I choose the power of 2 as 2, because if I choose 3 squared and do the first, you'll get way better, like larger number. So we are trying to minimize. So that's 60. So without having choices, you can use the counting divisor approach to get what you want as well. Anyway, so that was number 12. So the next question is geometry. We have 3x4 rectangle, and DC and BA is 1, CB is also 1. Area of the bat is what we are looking for. So like one of the things that we should probably see, like immediately, this is like 3 by 4. The entire region is like 12. And the area of ABF is 1 times 4 over 2, which is this region is 2. And the same region right here is also 2. And after this point, like another thing we can easily see, CEF as a triangle. So if I take the C and then drop the altitude all the way from C to EF, that altitude, which is height, is going to be the same as 4, which is like 4 as well. And then this base will be 3. So if you want to find the area of this, so you will get 3 times 4 over 2, which is 6. Another way to see it, this is actually area of the half of the area of the rectangle. The same story with BEF as well. So this is also 6 as well. So that should be B, E, F. This is also 6 because height is still 4, base is 3. So, and then this white region is common in these 2 triangles. So these 2 shaded region actually have the same thing, because if I say this is A, this is B, A plus B was 6. And then this region, this shaded region plus this B is also the same 6. So that's why this region will be A as well, which is something I'm not going to use in my like maybe solution, but it is good to have this in mind. What else we have? Like we have like 1 unit right here, so 3 unit right here. So if you take the maybe similar triangles into consideration, so we have like this guy right here, and then this guy right here is similar. The reason why they are similar because we have AD and AF is parallel, so that means the angle right here and the angle right here is the same, and then this angle and then this angle same, so that will be same as this one. They are vertical. Other two was alternate exterior interior angles. Now we know that this triangle and this triangle are similar and the ratio is 1/3. So that ratio should be the same for the other corresponding sides as well. So for example, if I take a look at this angle, that's opposite this segment. So if I name this as, let's say, X, and the same angle right here is on the other triangle is opposite to this segment, which has to be 3 times as much, which is 3x. So meaning that if I know this region was A, the base is x to 3x. So, and then this A and B has the common vertex of E. So when you drop the altitude from E to CF, that altitude will be height for these two triangles. So which means the base ratio will be area ratio since they have the same height. So if this is 1A in terms of area, and then this B should be 3 times as much, which is why that will be just 3A. So then I know 1A plus 3A is 4A. That should be half of the entire rectangle, which was 6. So then A has to be, we are looking for 2A, so maybe we can just divide by 2, which is going to give us just 3. That is the choice C. So we can do this question a couple different ways, but let me remind a few other things while we have this picture available. So A is like 3/2, and then this is 3/2, and then this is 3A, which is like 3/2 times 3 will be like it's equal to 9/2, right? And then since we know that the ratio was 1:3 for the bases, it's the same thing with this one. This is like whatever this is, it's going to be 1/3 of this segment. So if this region is 3/2, then this region will be 1/3 of this, which is going to be 1/2 for this region. Okay, so why this is kind of important, because like we can see that relation a couple different ways. One way is, you know, this region, this is 1/2, right? And this triangle and this triangle were similar, and the ratio was 1:3, so that's 3:1. And if you square this ratio of the similarity, which is going to be 9, so that will be area ratio. So if you know this area, you can just divide by 9 to get this area. If you know this area, you can multiply by 9 to get this area, which is, as you see, is confirmed. So if you take 1/2 and multiply by 9, you got this region. That's interesting. So we can use that relation of the similar triangles. And another thing we have in this figure, the product of these two like regions, like 3/2 times 3/2, is indeed this 1/2 times 9/2, which is not actually coincident. This is always the case. You can take a look at and prove if you can. That is always the case when you have a quadrilateral. Anyway, so I'm going to leave that as challenge. So that was number 13. So here's the number 14. It's a circle problem. So it's usually, we expect to see a lot of circle problems. So AC is 12 and BC is 5. C is a right angle. So we have a half circle inside. And we want to find the radius of this figure. Okay, so like we can try a couple ways. One way is like we generally approach, just start with finding your center and connect with some sort of intersection until you see nice figures. So if I connect with this intersection, so when you take the center and connect with the tangent line, the angle in between tangent line and the radius will be 90 degrees. And I don't know the radius. I'm going to call this is X. So that should be X as well. So meaning that this piece has to be like 12 minus R. So let's keep this invisible. And you know this is 5, this is 12. If you use the Pythagorean or Pythagorean triple, so that should be 13. And one of the key properties of the circles, when you have a point outside and draw two tangent line from that point to each tangency point, the distance will be equal. So this is 5 units, so that means this is also 5. So 30 minus like 5 should be 8. And now we have a right triangle because this is also 90, so we can use the Pythagorean. So if I use the Pythag, so you get 8 squared plus r squared is equal to 12 minus r squared, so should get 64 and r squared. And if you multiply 12 minus r by 12 minus r, you can just write it like 12 minus r and 12 minus r and multiply. Or you can just remember the square of binomial. So I'm going to use square of binomial. So that's the square of the first term. And then minus twice of the product of these two terms, which is minus 24r, and plus square of the second term. And I'm going to leave something about square binomial as well, if you need more practice about that. So that will be cancel each other. So then I have like add 24r to both sides. So you got 24r. Subtract 64 from this. It looks like we got 80. And divide by like maybe 4 before divide by 6. If you divide by 4, you got 20. And then divide by 4, that's 6. So that should be like 10 over 3. So that is choice D. So this is one thing we can do, but there are some other ways we can actually approach this problem. One of them is like, kind of reminds me immediately, when you have a circle inside of a triangle, we have something really useful as well. But even though in this case, it was not in the inside of a triangle, it was just half circle, not complete circle. But we can actually extend this. So if I extend this, same distance from like C to B, and then make this a complete triangle. So, and then imagine this is available right here as well. So you can just draw it if you want, but you don't need it. So if you have something like this, so regardless of the size or the type of the triangle, you actually can use this. This is 13, this is 13, and 5. So one thing we have is area of the triangle is S times R is going to be area of the triangle. So S is just the area of the S is the half of the perimeter, basically. S is equal to like A plus B plus C over 2. So in this case, 13, 13, and 10. So that should be like 13, 13, and 10 over 2. The proof of this is really simple. Like the proof is just this. You, like maybe I should kind of show it as well. So you take the center point and split your triangle into 3 triangles, which I will say this is 1, and this is 2. So when you draw the height, which is your radius, from that center to each side of the triangle, so this is 90, this is R, this is R, this is 90, and this is 90, this is R. So like you just find the area of this triangle separately. This is gonna be like R times this side, let's call this is A, over 2. And if I wanna find the area of this triangle, that should be like R times, let's say this is C, so that's C, over 2. And then if you want to find the area of this one, so you will get R times B over 2. When you pull the R over 2's, you will get, like maybe I should just take the R. If I pull the R, so you will get like A plus B plus C over 2. And then this quantity is named S, so that's going to be area of the triangle. So if you know this immediately, then you can skip all this red part. But now we can just skip, so that's 26, 36 divided by 2. Will be just 18, right? So that means S is 18 and R is what we are interested. Area, you know, this is height. So this 12 is height. The base is like 10. So 12 times 10 over 2, that is 12 times 5. So then R will be just like 60 over 18. Divide by 6, that will give us 10 over 3, which is the same result. So like you can use this or something else as well. But anyway, so that was our 14 problem. So let's see the next one. And we have point A is the midpoint. And there is a square. And we have diagonal and BE intersect at F. The area of the AEFD is 45. So this segment is same as this one. This is also similar to one of the previous problem that we did. And I'll just say, if this is like, since we do not know the actual numbers, I'm gonna call this like 1 and 1. This is just kind of ratio. This is 2. This is 2. You can say x to x, x to x, and stuff like that. And similar reason, ABF and CEF are similar, and ratio is 2 to 1. So if you have 2 to 1, that's like if you square this, you get 4 to 1, which means if you know this area as 1A, that means this region should be 4A. And that is something we just had in one of the previous problems. And if I connect this, because that will give us the similar figure, which is kind of interesting because this question was just really similar to the previous problem. Now this was missing. The other part was kind of similar. And since we know the ratio is 2 to 1, if this is 1A, so that means this is 2A, and then this is going to be the same reason as before. That's also 2A. And 2A plus 1A is 3A, so AEC has to be 3A, so that should be 3A as well, because this is midpoint. So the ADE and AEC has to have the same area. So now we are almost done. So we are told this guy and this guy add up to 45. And then A has to be just 9. And then we are looking for ABCDs. So that will be like 6A right here. So 6A right here, that's 12A. So 12A is 9 times 12, which is 100A. That's choice B. So like if you need a little bit more practice about the similar triangles, finding similar like triangles or using the area relations. So those are the two common like things that we always kind of see. So I will recommend you to look at those as well in the added like additional like videos in the description. Anyway, I'll see you in the next video.